in this section, we're comparing two dependent samples and match pairs. So again, we're looking at the hypothesis test to test claims about means. But when we say two dependent samples, we're looking at samples of two different groups where there's a natural way to pair the subjects in each group. And so two sets of observations are paired if each observation in one set has a special correspondence or connection with exactly one observation in the other set. Okay, and we'll look at some examples here of different ways that can be done. So in the following examples, we're going to state if the samples are dependent or independent, and whether or not the variable is quantitative or qualitative. That actually makes a difference here because generally when we're talking about qualitative data, we're going to be using proportions, whereas if we're looking at quantitative data, we'll be computing means. And in this example, among competing acne medications, does one perform better than the other? To answer this question, researchers applied medication A to one part of the subject's face and medication B to a different part of the subject's face to determine the proportion of subjects whose acne cleared up for each medication. The part of the face that received medication A was randomly determined. Now, in this case, let's identify what samples 1 and 2 are and what the variable is. Because in this case, notice that we're actually talking about qualitative data, because the data we're collecting is whether or not the person's face cleared up, which is not something that's measured, but rather is determined as like either a yes or a no, right? So either the person's face cleared up or it didn't. So that's qualitative data. And so we're going to be collecting the proportion of faces that cleared up for each different type of medication. So for the first sample will be those that that had medication A. And for medication B will be sample 2. Oops, can't spell it. And we're collecting the proportion of faces that cleared up under each medication. And in this case, because each person's face is both medications applied to it, these will be dependent samples, right? Because each person's face is a way of matching up a sample from each group. Since each person's face has both a sample from medication A and from medication B. In the next one here, a researcher wishes to determine the effects of alcohol on people's reaction time. She randomly divides 100 people 21 years or older into two groups. Group 1 is asked to drink 3 ounces of alcohol, while Group 2 drinks a placebo. 30 minutes later, they measure their reaction time. And in this case, our two samples will consist of one group that is asked to drink alcohol, and then a second group that drinks placebo. Okay, so the sample 1 would be the group that drinks alcohol. And the second group would be the group that drinks a placebo. and we're going to test their mean reaction time. So what we notice is that we're computing a reaction time, which is quantitative data. So we're looking at quantitative data. And because there's no natural way of grouping these individual subjects, or I should say pairing these individual subjects, these would be independent samples. In the next example, a statistician wants to compare the treatment of female and male actors based on their ages. She looks at the ages of the females and males who won Best Actor, Actress in the last 5 years of the Oscars. So in this case, our two samples will consist of males and females who won Best Actor and Actress in the last 5 years. So yeah, so actually let's group them up that way. So females who won Best Actress in one group, and then males who won Best Actor in the next group. And in this case, their variable will be their mean age. So their ages. And in this case, of course, their age is quantitative data. And actually, there is a natural way to group them up, because each year there's one winner from each group, right? So for instance, in the year 2020, there will be one actor from each group that's chosen. And so there's a natural way to pair them up. So I would say that these are dependent. Let's look at the basic idea of how we can combine our two samples of paired data into one sample that looks at the difference between those pairs. So consider an experiment where a researcher throws a stick towards someone and first asks them to catch it with their dominant hand, and then again to catch it with their non-dominant hand. And the times below showed how long it took several individuals to react to this toss. Now in our sample, we've got 12 individuals, and each individual has two pieces of data associated with them. One, the reaction time for their dominant hand, and another, the reaction time for their non-dominant hand. So are these dependent samples? Well, they're dependent because each subject has a pair of data. So there's a natural way that the data are paired together. And so to determine whether or not there's a difference between the dominant hand and the non-dominant hand, we're going to look at the difference between each. So we're going to subtract, in this case di, what we're calling di, will be subtracting xi minus yi. So to look at the difference between the data collected in this column minus the data collected in this column. Okay, so after we've looked at the differences, then we're going to run a hypothesis test on D. So a hypothesis test on the variable D. And D is just a single set of data now. Okay, so what we're calling mu d, so the true mean of the differences, is mu d, and that looks at the mean of this column here. And in this case, actually, that's a sample mean if we're looking at the data in this column, so that would be xd bar. And that would be computed by summing up all those values of d and then dividing by the sample size. And if we look here, we've got 12 individuals, so there's 12 differences. And here in the last entry there, they've given us the sum, which was negative 0.158. If we divide that by 12, we get our mean difference here would be negative 0.013. Sample size n, in this case 12 individuals, right? The sample standard deviation of the distance differences will be denoted as d. So notice we're just adding a subscript of d whenever we do it. Now what I called x bar d here, we can also call just d bar, would be another way to reference it, and that's I think what they use in the book. So it's the same thing there. So anyway, the same logic that we use in a hypothesis test for a single set of data for hypothesis test of a mean will be the same logic here. So in this case, we're always going to have our mu d equal to 0, meaning that there's no difference between the different pairs of data, whereas the alternative hypothesis would be something other than 0. So in this case, mu d is less than 0 would be the alternative here, but it could be greater than 0 or just not equal to 0. So if d bar is equal to 0, then of course we would not be able to reject the null hypothesis. If it's just a little bit less than 0, we still would not be able to reject, so we would fail to reject. And if d bar is greater than 0, we still fail to reject. But only in the case when d bar is less than 0 by a significant amount, then we can reject. And that's what we'll be testing when we do the hypothesis test, is whether or not d bar is less than 0 or is different than 0 in some significant amount. And of course the usual process is going to be applied here. First, we make sure that our samples are dependent and simple random samples. They come from a normally distributed sample or a large enough sample size that's greater than 30. The null hypothesis will always be of the form mu d equals to 0. We have a few different possibilities for the alternative hypothesis, but it's either less than 0, greater than 0, or not equal to 0. Our level of significance alpha will be 0.05 by default as usual. And our test statistic here will be using the t-score because here we're using the sample standard deviation. And it's just our usual z-score formula. Take the sample mean minus the population mean, which by assumption this is always 0. And then divided by the sampling standard deviation. And then of course we've got our three possibilities. For the p-value method, we're computing the area of the region on the left tail if it involves the less than 0. We're computing the value of the two tails if it's a not equal to 0. And we're computing the right tail if it's a greater than 0. And then we'll also look at the t-test when we're doing this. Notice this is the same one that we used when we had a single set of data, but the difference here is we're doing it with mu d instead of mu. So we're going to go about performing the test in the same way that we did before, but rather than using two separate sets of data, we're combining the data together into one set and then doing t-test. And so for mu 0, we're always going to use 0, right? So this value will always be 0 because it's mu d. And then the standard deviation of our sample, SD, the sample mean with d bar, sample size n, and then the form of the alternative hypothesis.